Excellent, thanks for that. So, title's on the screen already there. I'm going to talk to you a bit about laser ablation hafnium geochronology. So, an in situ technique. What I will do today is I'll talk a bit about the methods, but not too much. Hopefully, mostly spend some time on applications and see where this can take us to date, particularly metamorphic events, also mafic rocks, and a range of hydrothermal minerals as well. That's sort of the aim of the talk, more or less. So before I start, I also want to acknowledge the Garnet people. I'm in Adelaide at the moment, traditional custodians whose ancestral lands we gather on, or at least I gather on at the moment. Acknowledge the deep feelings of attachment and relationships of the Garnet people to country, and respect and value their past, present, and ongoing connection to the land and cultural beliefs. Okay, quick outline of the talk. So as I mentioned before, a bit about the methods, not too much in detail, but at least give you the main sort of principles about how it all works. Also a bit about how we calculate dates using this beta decay system. A little bit about what kind of ref materials we use as well and how that works for calibration purposes. And then I'll go through a bunch of minerals that we developed with the methods, trying to illustrate what we can do with those minerals in this space. So garnet lithium hafnium dating, focusing particularly on application to date polymetamorphic histories. Apatite, I'm going to show how hafnium and lead dating can give you different results and what that might mean potentially for your rocks that you have. Carbonates, so we can also date carbonates with lithium hafnium, some examples from carbonatite systems and also IOCGs. And then also fluorite, same idea, just a bit about how it works and then applying it to an IOCG system. And then at the end, just one slide on ongoing developments on dating epidote and allanite as well. That's kind of the broad outline. Okay, so the method, how does it work? Here's an example of our laser system in Adelaide. Here's a bit of thin section. We can see we're using a pulse laser here to ablate an apatite in situ. The little particles travel through some tubes, reach the plasma where they get broken down to their atomic proportions. They get ionized and then travel towards the mass analyzer system. So we're using an Agilent 8900 mass spec tandem mass spectrometry. So which has basically two quadrupoles, and between those two there's a reaction cell. And that's then the main thing where all the magic happens is inside that reaction inside that reaction cell, where we pump ammonia gas, which reacts with hafnium, but not with lutetium, and that allows us to separate those same mass materials. So the parent and the daughter have the same mass in the system here. Lutetium-176 decays to 176 hafnium. Hafnium reacts with ammonia gas, lutetium doesn't, so we can separate them out in that reaction cell and analyze them separately. What we can do as well, either on the same ablation targets or perhaps even more relevant on an ablation target just next to it, we can also extract some rhenium lead ages from the same materials as well for cross-checking or to see how the methods compare to each other. The key thing is that it's a very fast in situ method, so we are dating within petrogenetic contexts, and the acquisition of data, particularly for lithium hafnium, is very fast. So a bit more detail, if you zoom in, if you like, inside this mass analyzer system and sort of show the flow paths of those different ions that we measure. So we're interested in those three components, which is your daughter proxy, which is 176 hafnium, the parent, 175 lutetium. You know it's 175, not 176, and there's a reason for that. And then the non-radiogenic initial hafnium system, for which we measure 178 hafnium, okay? So these two bars here are the two quadrupole systems, and the green box in between them is the reaction cell. So if we want to measure 176 hafnium, we let through in the first quadrupole system only ions with mass 176. That is hafnium plus lutetium plus ytterbium, and they all go through at the same time. They reach the reaction cell, and from those, only hafnium reacts with the ammonia gas to form this large cluster ion, which shifts the mass to mass 258. If we then select on the second quadrupole, mass 258, we're getting purely hafnium 176 into our detector and no longer lutetium. If we then cycle by changing those voltages on the quadrupole systems to just measure the parent, we put both mass analyzers to mass 175. So lutetium does not react with hafnium. So sorry, with ammonia gas. So it goes straight through as normal. And then same deal for the initial hafnium composition. So we measure 178 hafnium by putting the first quadrupole to mass 178 and the second one to mass 260, which is the same offset compared to the previous one, plus 82 AMU. That's kind of how it works. So we're chemically separating those different products from each other. And by cycling rapidly through those different isotopes, we can independently measure them on the detector. So a bit more detail about the method can be found in this paper here if you're interested, sort of quite detailed on the approach, also on all kinds of correction factors and things required, as I'll explain in this paper. I'm not going to go in much more detail on the methods. I'm just going to show you, I guess, which minerals we can date now with this particular methods, or at least that we have developed so far. So the first paper, we developed garnet, apatite, and xenotime as the main minerals. Second paper, we looked at carbonates, particularly calcites, but now we're also dating dolomite, siderite, and basanesite as well with the methods. Basically, any carbonate that has rare earths in it can be dating. Fluorite was sort of beginning of this year, and then we're also in progress testing on epidote, allanites, and monazite. And I'll show you some examples of all those systems in the next few slides. Okay. Now, before I start going through different minerals, I kind of want to show a bit about how we calculate dates. How do we measure things? How do we calculate dates? And a bit more sort of textbook theory to get you all on the same page. So there's sort of two types of minerals. There are minerals that take a little bit of initial hafnium in their crystal lattice when they grow, and there are minerals that don't like initial hafnium. So the one that I'm showing on the screen here now are those that don't like initial hafnium. So particularly calcites and most felsic apatites, they don't take hafnium in their crystal lattice. And that's mostly because things like zircon co-crystallize. So all the hafnium goes into the zircon, for example, right? Which means that the other minerals that take lutetium, they don't take the hafnium. So at the starting points, the minerals have just lutetium and no hafnium. That's almost like the ideal case, if you like. So in our hour watch here, we have a bunch of lutetium inside the lattice. There's no initial hafnium. And then we start, the 1 billion years clock here starts ticking. Some lutetium decays, becomes hafnium. And by analyzing the ratio between those two, we can get an age for every single ablation target. Okay, because there's no initial hafnium here. So we just measure that ratio, and from that ratio, we can get individual spot ages. And then if you line up all these spot ages, we can calculate the weighted mean through that. They should all have the same number, ideally, and we can then sort of calculate a weighted mean age based on X number of analysis on that mineral, okay? So here's an example of apatites that gave an age of 1097 plus minus 5 million years with the method. That's obviously the ideal case, but there are other systems, particularly most garnets, apatites in mafic rocks that don't have zircons crystallizing with them, for example. They already take hafnium before the clock starts ticking. So they have initial hafnium already inside the crystal lattice. So what we do here then is we use an isochronology regression to calculate the age, because every single crystal will have a variable amount of initial hafnium inside it. So at time 0, there's 3 different crystals here. They will have some lutetium in them and some hafnium, but the amount of hafnium is variable. Just depends perhaps when that crystal grew and how much it took in. So it's variable at time 0, okay? If we now start ticking the clock again, so the 1 billion year clock starts ticking to 1 billion years, you will see that all these points here, they move in this plot towards a different position. And they're doing that systematically. So lutetium was decaying, made radiogenic hafnium, and the total amount of hafnium, if you like, dictates the position of those spots, of those 3 different points in this plot. So they form a nice line if they have the same age, and the age can be calculated by the lower intercepts at 0 common hafnium, basically, because that's the same thing as you would have no hafnium in the system, okay? So by putting a regression to those different points, we can calculate time based on this line here. Doing this again, if we start, the clock goes a bit further up, go to 2 billion years, more hafnium has accumulated, everything is shifting on the x-axis this way, and again, by regressing a line through that, we can get a number. So in the next few slides, you will see either weighted mean plots for minerals that have no initial hafnium, or isochronology regressions for minerals that have initial hafnium. And that's sort of how we calculate the numbers from that. Okay. All right, let's go now through some of our ref materials so that we use for calibration purposes. At the moment, there is no natural material that is homogeneous enough that we can use as primary, as in the primary that we use to calibrate for drift issues and to normalize against. So we still use a glass, which is in most cases NIST 610 to do our primary calibration too. But because the matrix of a glass is not the same as a garnet or an apatite or a carbonate, we have to use a different standard to calibrate for what we call matrix-dependent fractionation. So the ratio lutetium to hafnium is also dependent on the matrix. Okay, so here's an example for garnet, and the same material here, and this is our calibration standard for garnet, had been measured over 5 sessions, and these are all color-coded. You can see they're quite consistent, and we can put a regression line through those to calculate the age. But the age here, the measured age, is not the same as the expected age. There's an offset, and the offset is because we are calibrating a garnet against the glass. Now, based on the difference between the measured age and the reference age, we can correct our data. So this is the offset factor over here, and apply that to our unknowns. And by doing so, calibrate secondarily to a garnet standard as well. So the process is going to involve 2 steps almost. You calibrate for everything required in normal geochronology, if you like, so drift and so forth against the glass. And then there's a secondary calibration required to calibrate the lutetium hafnium ratio to be appropriate for that particular mineral. So for garnet, we use Hogsbow as currently. This is reference age, quite well constrained by cogenetic columbites. So that's our reference age for it. For apatites, we use a sample from Olympic Dam in most cases as our primary calibration standard, I should say. You can see the measured age over multiple sessions, low scatter, is about 1660 more or less, and as the reference age based on an age that's been published by J. Thompson a little while ago. So again, we apply an offset factor, and you can see they're quite similar. So that is telling us that apatite and garnet don't fractionate much differently compared to glass. But this is for calcite. For calcite, we use MKAD calcites, for which we have a very good titanite age, and again, they're cogenetic. And the measured age on their calcites is slightly less offset compared to what we see in apatite and garnet, for example. So it's really important to do your matrix matching when you calibrate. So here you can see we didn't use an isochron because there was no initial hafnium in the calcites. So we can do purely single spots, dates, and then calculate the weighted mean to work out the age of that particular calcite. Okay. Obviously, when you calibrate, you have to cross-check to make sure that what you're doing is accurate. So in every session that we do, we also analyze some secondary standards. So in terms of garnets, our go-to one is called Black Point 1 from a place out of Australia. We know the age very well based on a TIMS hafnium age, based on a monazite age. And as you can see, over 5 sessions, we get a nice isochron with a garnet age that is pretty much well into agreement with the published numbers. So this means that our calibration works well for garnet. For apatite, we use BAML as our secondary, and we get a good age here of 1097 over multiple sessions, which again is in good agreement with published numbers for the apatite. And then also lastly with calcites, going through all the steps, this is our secondary calcite standards. We've got a good age that again is also conformed with previous numbers. So we analyze those every single session to make sure that our dates are accurate, and that's quite important. All right, let's now go through some examples, mineral by mineral. So the first one to talk about is garnet. I can probably talk a whole session about garnet because we've got a lot of dates and a lot of things that we've learned about garnet, but I'm going to keep it quite simple today. I've got here a probe map on the screen, and the probe map, I think it's for calcium. It doesn't really matter what it is. It shows that the one garnet is clearly not one garnet. It has clearly a rim zone in yellow here and a purple area in the middle with a different composition. So rather than being a single garnet, it's probably one garnet and then a new garnet that grew over it afterwards. So if you would want to date that in the traditional way with either SMND or lutetium hafnium, by the solution. You'll take the garnet, you dissolve it. What you might expect is an age that is mixing between those two different domains, right? If those two domains grew very shortly after each other, then there's no problem. But if they grew at different times, then you will get a mixing age that is maybe meaningless. So in these particular cases, the in situ methods can be very powerful, because what we do is we don't dissolve the garnet, we target those zones independently with a whole bunch of spots and can get an age for the rim and the core, just like you do for zircons, for example. By doing so, this is an example from O'Larry in South Australia, and we got these beautiful ages. So you can see for the rim, we get this array here that gives an age of 514 with a reasonable uncertainty. And for the core, we get an age that is very different than age, 1613. In other words, this garnet has grown 2 times. It has made the first garnet during the O'Larrian orogeny, and that's exactly the number for that. And then during the Delamerian, an overprint happened after that. So we can separate those two and get resolving of polymetamorphic histories essentially directly from a rock block or from tensection, because the ablation depth also allows for garnet to be used in tensection as well. So we usually take 10 sections, put them on the laser, and we can date those different generations directly in situ. And that's, I think, one of the most powerful ways of dating garnet with this method. However, another way you can do it as well is dating pegmatites that are very rich in rare earths. So these pegmatites commonly also have zircons, but these zircons are also commonly metamorphic and cannot be dated easily. Shrimp might give you some success, but with the laser, it's usually almost impossible to date those zircons. Now, some of those might have also garnet in them, so we can then use maybe the garnets to get the nature of the pegmatites. Here's an example from a pegmatite field in Tordal in southern Norway, kind of known for very high rare earths compositions, also very high scandium as well. I think they're probably getting mined soon for scandium, these ones. So here's an example of an isochronological regression from one of these garnets. Here's an example of an image, an SEM image of one of those garnets. I want to draw your attention maybe first to this point here. The composition of lutetium in the garnet is super high, up to 8% lutetium. So we get an enormous amount of lutetium in the garnets, which leads to very high count rates and by extent, very good precision. The precision for this single isochron in one session is already better than 0.3%. So we get an age here of 925 plus or minus 2 million years. Now, the same sort of garnets are dated several times to understand also a bit of, I guess, how reproducible our dates are. And over multiple sessions, we're getting these values here. So I've taken this cluster at the bottom here, which is very radiogenic, and I've calculated single spot ages for all those, and just line them up over different sessions. As you can see, there's not much variation between sessions, and you can put a weighted mean through all those points over multiple sessions with an uncertainty of 1 million year and an age of 930 plus or minus, and an age of 931 million years. In other words, precision can be as good as approximating 0.1% for those garnets. So for certain questions where you need very high precision, this method can also be powerful. However, in most cases, you will not achieve that, because in most cases, garnet has far less lutetium than this, of course. So keep that in mind. But if you want to have detailed, high precision numbers, then the method can potentially also achieve that as well. All right, let's go to apatite then. So I'm going to spend a bit more time on apatites because that's probably a bit more new, perhaps, to the community. I've got a rock here from a place called Taratap in South Australia. It's a very simple looking granodiorite consisting of quartz, plagioclase, clay feldspar, biotites, and accessory zircons, apatites, monazite, and titanite. So a lot of things in there we can date, and that's why we've chosen this rock, because we can cross-check a whole bunch of methods against each other to see which ones behave, I guess, differently or comparatively to others. Also, we have a very good zircon TIMS age for this rock, so we have a very nice reference point to work against. So the age of the zircons in this rock is 497 plus or minus 0.1 million years, okay, by zircon TIMS. All right, we're going to date almost every mineral listed here, not quartz. That's one of those few minerals we can't date yet, maybe one day. But all the other ones listed here, we're going to use for dating purposes. Okay, so monazite date with indirect methods. So get an age that is the same as zircon age with an uncertainty. This is a biotite, K-feldspar, plagioclase, in situ RBSR date for the same rock, and we get again the same number with uncertainty to zircon age. And to show you, I guess, the relationship between biotite, apatite, monazite, you can see, well, based on knowing these values, I'm sure you can already guess what the age should be for apatites. Monazite is overgrowing apatites and then sitting in a biotite, which we have dates for. So surprise, surprise, the hafnium age for apatites is again the exact same number as those above, which means that that's all happy days. Apatites confidently constrains the primary magmatic age of this rock, just like zircon does. Okay, nothing new there. However, what happens if you then use the same apatite grains and apply the apatite uranium lead method? What we get is this. It's an age that is younger compared to the hafnium age. So it looks like that in the same grains, the hafnium and lead system have been decoupled. And that's quite important to understand, because that means that if you would just have apatites and perhaps no zircons, and you apply this method, you might get an age that does not give you the age of magmatism. It might give you a secondary age. There's also some titanite in the rock. Not very happy looking titanites. So here's a bit of a thin section image. All these little circles are the ablation targets. It's very strange looking titanite, perhaps. It's secondary clearly. And if we date those, we get two populations, a population of around 507 plus minus 10. So in agreement with zircon age, but also a population that's much younger, which is the same number more or less as we're getting for the apatite uranium lead age. So if you put it all together in a bit of just a simple graph here, we're seeing that most clocks date magmatism, but there's clearly a secondary event that has affected the rock. I've put it here as some sort of hydrothermal events because that's what kind of how the titanite looks like between brackets. But clearly some of that has also affected the apatites inside the same rock. Key point is that apatite hafnium system remains robust to whatever that secondary event was. We also did some titanium in quartz thermometry. Very briefly, just using titanium concentration in quartz, we can work out temperatures of when these quartz have been crystallized. And you can see some quartz remain uncrystallized, sort of magmatic temperatures, but some go down all the way to about 430 degrees, which means that the EPB system probably has been reset, likely by volume diffusion, in response to those temperature system that was acquired sometime after magmatism. In other words, it's probably a cooling age of some sort, and therefore not necessarily a useful number, while the hafnium system gives you the primary magmatic age. All right, next study area. We're now going to Northern Territory because I guess we're talking to people from Northern Territory. I'm not going to say much about the study area because I think you know more than I do about it. But here we are in the Reynolds Ranges, and this is a batholith that's been exhumed differentially, preserving sub-greenschist fascist conditions in the northwest and all the way to granulite conditions in the southeast. So it's a perfect system to evaluate how different minerals respond to differences in metamorphic grades within a single system. So we took samples all across the grades, not all the way to granulites because that was getting too hot for us, but at least into upper amphibolite facies. And importantly, there's also two different rock types. We have gneisses, so deformed rocks, and we have granites that are unfoliated. And we have a reasonably good understanding of how old these rocks should be based on zircons. So we dated the zircons from the same rocks we analyzed, and they clustered around 1.8 roughly billion years. That's sort of how old the protolith of the rock is. But we also known, based on a whole bunch of data sets acquired over several years, that there's been secondary events after magmatism. Obviously, metamorphism has happened afterwards. Deformation, high temperature metamorphism, and there's some pegmatites in the area as well. And that's roughly sort of these bars here give you the timing of when these things have happened. That's what we know about the study area. The samples that we've taken, so all the gneisses here are in the amphibolite facies system, and then the granites, we took one upper amphibolite facies rock and one sort of greenschist facies rock, or maybe not even actually, a very cold rock compared to the previous one. So, okay, what we expect to see is that apatite might have crystallized over here in the gneisses, but should be primary in those rocks that are unfoliated. Okay, what we get in terms of age data then. So this is where our apatite minimum lead date plot for those apatites in those 5 rocks. You can see that the granites, they date the time of metamorphism. So that is useful to some extent. And for those rocks in the gneisses, we get cooling ages that somewhat relate perhaps to those pegmatites intrusions. So clearly they're very different to their primary zircon ages in the same rocks. What about hafnium then, you might ask? That's how hafnium looks like. In the gneisses, we're dating the timing of the formation, while in the granites, there's some small offsets, but with uncertainty, we have the same number as the zircon ages. So what does that tell us? That tells us that based on the temperature conditions of these rocks that we have over here, the hafnium system remains robust, temperatures at least over 660 degrees, while apatite lead system in this particular system here has been reset at temperatures even below 450 degrees. However, if the rock is foliated, apatites recrystallize quite easily, and therefore you are, if you like, resetting the clock at the timing of the formation. So the timing of new growth, that's what should be dated with the hafnium system. So in a gneiss, in a rock that has been deformed, at least strongly deformed, where apatite is clearly regrown, you would date the timing of the formation. In a granite, where apatite remains primary texturally, you will date the timing of primary magmatism, even when it has been through amphibolic conditions afterwards. Okay. All right, now this is also all felsic materials, where apatite is quite abundant, and there's also zircons. So you might ask, okay, there's zircons in the system, so why do we care apatite? Which might be, that's a good question, perhaps to some extent. But there's also other rock types, particularly mafic rocks, where zircons may not be abundant or even completely absent. So this is, I guess, where apatite hafnium dating might potentially be even more important. So an example of that, we went to the Finland-Scandinavian Shields in Finland, where there are some mafic rocks. So there's a layered mafic intrusive system where we have gabbros and gabbronorites. And there are zircon dates in the vicinity of rocks that are supposedly cogenetic with those rocks. And they have these numbers here, so the Svecofenian orogeny. And we also know that the sample have experienced amphibolic conditions afterwards. That's kind of like our framework. And on the screen here, so there's 2 samples that we dated. You can see we have apatite lead ages that are clearly younger than the reference ages for zircons in those rocks. So 1714, 1782. Hafnium, on the other hand, gives these numbers. So 1907, 1899, well within range of zircon ages. So again, this shows us that apatite hafnium can robustly date mafic rocks where apatite UPB fails, at least in this particular case. So a bit of a summary, I guess, for the study area. So these are the zircon ages here. These are apatite hafnium ages, and these are UPB ages. So clearly, the lead ages have been reset somehow after formation. All right, then the question can we break the hafnium system? So how hot can they survive to? That's the other thing to test. So we went to a hot area, back into mafic rocks. We're now in the Yilgarn, and these rocks are gabbros. We've got quite good Bedelia ages for the gabbros as a reference point. And we know that these rocks have experienced lower granulite facial conditions. So temperatures between about 700 degrees and 745. So here's a PT pseudosection, sort of shows which mineral is stable at that time, and temperatures from that can be calculated to be roughly around sort of that bracket. So the rocks that we analyze have seen metamorphism at those temperatures basically after they formed. So this sort of graph here just gives you the ages again and the main events in the study area. So magmatism based on the bedeliites is 2.65 roughly. We have the Albany-Fraser orogeny in the area that might have caused that high temperature fields that we're seeing in the rocks. And there's also the Kunga as well afterwards as well. So these are sort of our main sort of secondary events that happened after formation of these rocks. All right, so this is how our apatite EPB data looks like. So you can see for one sample, we get a lovely Kunga date. And for the other sample, we get a bit of a mixing between an array that sort of goes to a roughly an Albany Fraser age and a younger array that goes through Kunga age. So clearly, apatite lead system has been reset after formation, and depending on the sample, depending on the conditions, you might either get Kunga ages or Albany Fraser ages, or somewhere in between. What about hafnium then? So remember, these are very hot systems. It looks like in one sample, this particular one, we are nicely dating the timing of Albany Fraser. So it does not care about the Kunga, which must mean the Kunga is probably colder, but it's dating the timing of the Albany Fraser, which is likely the high temperature field that we just experienced. And the other sample, more interestingly, some grains seem to preserve magmatic numbers and some are being reset towards the Albany Fraser as well. So what it turns out that at those sort of temperatures, roughly sort of 700 to 750 degrees, we are partially resetting the hafnium system, potentially also completely, but we might have some preservation of some old dates as well. So at those temperatures, the hafnium system is likely to break. So granulite facies is probably getting too hot to be retaining primary numbers. But anything upwards towards that is probably fine. Now, just to finish off apatites, last slide on that, to further test, I guess, the robustness of the methods, we also looked at some xenoliths. This is in a young basaltic melt in Queensland, where we know that the basalts are very young. They erupted at around sort of 3 million years ago. We try to date apatites by EPB system. As you can imagine, we get nothing useful out of that. So that can be either tomorrow or yesterday. It's just very young. But if you look at the hafnium system, then we get this little complicated graph. So I'm plotting here single spot ages on the x-axis versus grain size. So we have a whole range in grain sizes, from very small grains to very big grains. And what you can see quite nicely here is there's a bit of a trend that shows you if you have large grains, we start to preserve an age that is clearly older than the eruption age. And if you go to smaller grain sizes, you go all the way to close to zero. So the small grains have been re-equilibrated to the mafic melt, while the older grains are telling us something about their residence in the lower crust before they got erupted. So you might actually get information about what's the lower crust composed of, as using the apatites as a bit of a probe, if you like, for that. So after transient residence, and these are very hot basalts, 1200 degrees roughly is the melt, complete resets of the EPB system, but the hafnium system preserved in large crystals. So we can use xenolith systems as well, potentially to look at the lower crust. All right, that's apatite for now. So as you can see, very useful, perhaps, to date certain questions you might have, where other methods might fail. Now I'm going to move on to the next mineral, which is calcite. Just a bit of a summary, I guess, of our recent papers, if you're interested, that detail, I guess, most of what I've talked about so far. I think this will be available to you as well anyway after the recording, if you want to look back at those, to look up some of those papers. I'm going to calcite. So calcites, platform calcite, for example, you can't date hafnium because they have no rare earths in them. But you can imagine the fluids in a mineralized system that makes calcites, they might have rare earths in them because rare earths might be available in that fluid. So here's an example of a rock from the Mount Elliott IOCG in Mount Isa, where we have a very good reference age based on a Morley age from Rob Duncan, 1550 million years. And the rock is composed of calcite in pink. It has lovely big androdites, garnets, these are the blue things here, some hematites and some pyritites. So it can be used almost to try to date those pyritites if that's of interest. All these black circles here are our ablation targets in the calcites. But before we look at the calcite data, we also dated the androdites to make sure that we have in the same rock a reference point basically to work against. So the androdites gave an age of 1507. So androdites have uranium a bit in the lattice, so they can be dated directly by UPB. And the age here is with uncertainty the same as the reference age for the osmium. So we know that the calcite should be roughly about that if it works. So hafnium and calcite, here we go. This is our age for this rock. We get an age of 1513 plus or minus 12 million years. So even better uncertainty than did in the andradite, and very well matched with Rob Duncan's age on the Molly, which means that it works, which was quite happy if we saw that. So we can date calcite in situ in a mineralized system potentially. Another example, we're now in Palabora in South Africa, looking at the carbonatites, where again, calcite is quite abundant. And if you want to date carbonatites, then you may as well try to date calcite. So we have a good reference age as well here. It's a bedillite age of 2047, published several years ago. And this is how the rock looks like. So you can see it's abundant dolomite and calcite, and also a lovely large chalcopyrite vein through it. So if you want to date the copper, you can date the calcite potentially, and you will know how old the copper is, if those two are cogenetic, which seems to be the case in this rock. So we did that. We tried to take the calcite, and we got an age of 2049 plus or minus 25 million years. So not as good uncertainty as the one that was previously published, but you can see very accurate, same number with uncertainty. So it can also be used to date carbonatites. And we've managed to date a couple now so far. I've only going to show you one example today, but we've got some more as well that we dated recently. So that's happy days, that works well. I'm going to bring you to a bit of a case study where we applied apatites and carbonate dating to a single prospect. So it's a prospect, an ICG prospect in the Gala Craton. As of most prospects in the Gala Craton, expected age is Olympic dam age, 1590. That's sort of our reference age that we're hoping to get. And it's just two samples from the drill core that we analyzed. The green stuff is apatites. So we analyzed the apatites both with hafnium and with uranium lead dating. And as you can see, we get numbers that are pretty close to what the expected age is. However, if you compare the left column to the right column, so the lead versus hafnium dates, you can see that the lead ages are sometimes a bit too young and sometimes have very high uncertainties because there's not much uranium in it. However, the hafnium dates, they give precision is slightly better, not compared to that one, but compared to this one at least. And accuracy is definitely not compromised. So we're getting the right age, if you like, compared to the expected age. So although both systems probably work in the system here, I would say that hafnium is slightly more accurate compared to lead dating. But perhaps what's more interesting is to look at what does calcite do in the same rock system. So this is not the same rock, but I think a bit deeper down into the drill core, and you can see a lovely bread shaded system that has some large blocky carbonates in them. And it's not anymore calcite. Here we've got dolomite, which is the dark blue, and some siderite, which is the sort of light blue purple color. And apatite as well. So apatite is the same as I showed you previously. Let's see how the carbonate ages look like. Dolomite gives a lovely age of 1580 plus or minus 34, which is in agreement with the apatite age and with the expected age, which means that we can use dolomite to date potentially mineralization. Siderites needs a bit more work. There were not many targets that we could use unfiltered, if you like, because it had many inclusions. And as you can see, the age has a big uncertainty. It's still in agreement with the expected age, but it's probably slightly too young. So we need a bit more work on that. My expectation is also that we're using a calcite to calibrate a siderite, which is maybe not necessarily appropriate. So we might need to find a siderite calibration standards in the future to make this work better. But in any case, it looks like the carbonates can be used to date this particular ICG system and that fluid. However, there's also some younger looking carbonates in the same rock system. So you can see here some lovely examples of younger calcite and dolomite that clearly have copper inside them. So it looks like copper has been transported in these younger veins as well. So if you can date those veins, you can date potentially a secondary event that might have moved the copper, or potentially even organized a concentration of copper somewhere higher up in the system. So it can be very powerful to date those calcites to work out how that copper behaved. And so we did. So we get dates for the same drill core as the one I showed you previously that are much younger. We're getting here Ediacaran ages, 560, 570 million years, consistent with each other, but definitely much younger compared to what we saw previously. So a question I guess I pose here is that perhaps we are looking at a vein system that has moved copper from basement to cover in the new Proterozoic inside the overlying sequences, which is quite nice. But obviously more data required to really firm this. All right, next mineral on the block is fluorite. So as with every mineral that you try to date, you want to go first to a place where you know a lot about the existing rock. So you have previously age constraints, or there is minerals inside it that you can date as well. Which brought us to the Pilbara to look at some rocks that have magmatic fluorites, which is quite rare, but they do come across sometimes. So we're in the Pilbara here, and we took a rock from the split rock supersuite. It's a Monzo granite that had both garnet and fluorite inside it. And as you can see here, we dated the garnet, gave a lovely age, beautiful isochron, 2.8 plus or minus 11 million years. So very nice, precise isochron for the garnet, which fits very well with what we know for the rock as well. And then the fluorites, again, gave the same age with uncertainty. So 2.86 plus or minus 23 million years, and again, plus or minus 20 million years. I've got two uncertainties here. One of them is the uncertainty just based on the data itself, and the second one is propagated also the calibration standards inside it. So that's the one you want to use when you're reporting your data, basically. So quite nice ages. So this could potentially be used as a potential standard for fluorite dating in the future, or at least as a secondary standard to check your accuracy. So it worked, the method on fluorites. That was good. We then applied it again to a study area where fluorites might be quite powerful to date mineralization. So we're back in South Australia, got a craton, and we're going to look at two places, place A and B on the map here. Place A is Torrens Dam prospects in the IOCG system, so in the Olympic province. And then place B is actually fluorites in the cover sequence, and see if they give same or different ages. So inside the prospects, let's call it the basement if you like, we get fluorite dates of 1588 plus or minus 19 million years, which is the exact same age as Olympic Dam, which is quite nice. You might say, okay, that's great, but why fluorite? Well, fluorite has fluorine in it, of course, in it, and fluorine is an important ligand for metal transport. So if you date directly fluorite, you directly date the fluorine ligand basically as well. So that's quite handy. So that's the age for the basement rock, and then the fluorites in the overlying cover sequence in location B, so sandstone unit in the superbasin above it, gave an age of 502 million years. So what that potentially might mean is that we are dating an event that has transports, I haven't said before, but again, there's copper inside these fluorites, so you're transporting copper as well in those fluids. So we might be dating that transport from copper from the basement towards the cover. And this number here, 502, is not new. If you look at some of Kathy Eric's papers, you might see that that's the timing of upgrading, as she calls it, in Olympic Dam, based on some uranite ages. So we are potentially seeing something quite similar here as to Olympic Dam, as in which we made copper at 1588 and perhaps moved it at 500. And that's what these fluorite age also confirm nicely. All right, to finish off, I think my last slides, or second to last slides, we're also now working a bit on trying to date some, I guess, low temperature metamorphic minerals, so allanites and epidotes. It's work in progress. We had some success and some work needed, but here's some examples of allanites that we dated previously. This is one is here from Greenland. It's used as a ref material for allanite lead dating, and we got an age that is actually better than the, well, not better, but very close to the TIMS age for the same material. So 266 plus or minus 126, compared to 94 million years from about the same age. So we're quite confident that it can work on allanite. And then here's another sample here from a Chinese deposit, magmatite system, where again, we've got an age that is well in range of the expected age as well. So uncertainties are a bit higher, and that's mostly because there's a more initial hafnium in the system compared to most other minerals. But we've got some data, not on the screen here yet, that can show we can also date with relative good precision allanite systems as well. But hopefully in a future talk, I'll talk more about that. Then lastly, epidotes. So epidote is hard to date by any methods, and also for hafnium, but there are certain special cases where epidote dating works very well. I've got here a rock that is a mafic rock with large vesicles inside. And these vesicles have an infill of calcite, as you can see here, and the margin around them have epidotes. So that green stuff is epidote. We dated the calcite infill with hafnium, and we get an age of 497 plus or minus 19. We dated the epidote rim with hafnium, and we got an age of 497 plus or minus 23 million years. So beautifully matching with each other, which means that, okay, if we've got a mafic rock with vesicles, and these vesicles have been altered to epidotes, which is rather common, we can potentially use that as a way to date mafic rocks in the future. Now, although epidote works in this particular case, we've tried a whole range of systems that grab epidotes. And I can say that porphyries, for example, is not going to work because there's just way too much epidotes. So any kind of green rock is probably not going to work because the lutetium gets diluted over the entire system, and therefore you can't target it. But in cases like this, where the epidote is only growing in the margin around the vesicle, for example, and all the lutetium gets concentrated inside that, it might work. So just keep that in mind. If you're thinking around dating copper deposits with porphyries, that's probably not going to work. We've tried it, and not a single sample gave a useful number, unfortunately. So not everything works. All right, conclusions. So I'm hoping that I've given you a bit of an overview of what we've done so far, and illustrate some potentials here. We get very fast data, particularly if you compare to dilution methods. Preparation of samples is quite trivial. We can work directly from thin section in most cases, or from rock chips. Carbonates and fluorites, they ablate very aggressively. So that can't be done in situ in thin section, but it can be done from rock blocks. But things like garnet apatites, what else? Most epidotes can be done from thin section directly because we don't go as deep. All the data can be collected directly in context of your petrology because you have your thin sections there or your rock blocks. So it opens a whole new window to data mineralization. And the minerals that we currently have, I guess, applied this method on are growing, but these are the current ones. I think I've showed you also that in mineral systems that have both uranium and lutetium hafnium might be more robust. Apatite is the main one to illustrate that. But I can show the exact same thing also for carbonates as well. So calcites that are dated with uranium lead can give potentially a useless number, but then with hafnium give a right number. And also we collect a whole bunch of trace elements that we use for triaging our data, so to see any zoning, but also inclusion and so forth, which is harder to collect with the solution work. Obviously, there are challenges. The biggest one potentially is the requirement for large beam sizes. We commonly use beam sizes of around 100 microns for most minerals. Can go down to 67 as well in certain cases. So that's way bigger than your traditional zircon dating, for example. And particularly for carbonates and fluorites, we use monster spots of 250 micrometers because we need to have big spots to get enough counts. In most cases, that's not really a problem because usually fluorite and calcite are quite big, so you can put big things on them. But keep in mind that if your rock that you want to date is very fine-grained, or if the mineral of target is quite small in size, it may not work because we need bigger spots compared to, I guess, most traditional dating methods with laser. Also, it's a very long decay system, so about 37 billion years, so it's not really suitable for dating very young things unless you have tons and tons of lutetium. It's always a balance between having enough parents and enough ingrowth time. So if you have high lutetium, and it's a young system. It's still possible to date potentially, but and vice versa. If it's very old, you don't need as much lutetium to get a date. So that's worthwhile keeping in mind as well. It's really mostly suited for dating older history.